Hi everyone. In a previous lesson, we introduced while loops in Go, which keep performing some instructions for as long as some condition continues to be true. In this installment of Programming for Lovers, we will learn how Go implements a second, critical type of loop called a for loop. We will then apply for loops to make an alternative function for computing n factorial. Along the way, we will revisit a phenomenon called overflow, in which a variable's value exceeds the space that is allocated to it. And most importantly, by the end of this video, we will have all the fundamentals that we need to start building the key algorithms of this chapter. Efficient approaches for computing a GCD and finding prime numbers that date back over 2,000 years. As always, if you enjoy what you see, please like, subscribe, and join our course at programmingforlovers.com. Let's code. To get set up, I'm just going to continue editing the main.go file within the loops directory that we worked in the previous code along. So I'm assuming that you followed the previous code along on while loops, and there's no real reason to add a new folder for for loops. So I thought, well, let's just put all of our code in the same file for this code along. You'll also notice that I have the pseudocode for another factorial, which is a different way of writing a factorial function using a for loop. And that's where we're going to get started in this lesson with looking at for loops in Gauss, understanding their syntax, and implementing this function. So let's start there. We're going to look at another factorial, and I'm just going to say another factorial, which I am really struggling to type. Another factorial takes as input an integer n and returns n factorial. So the function signature of another factorial should be another factorial of n int, and it's going to return an integer as well. So to write another factorial, we want to do the same type of thing that we did previously. We want to make sure, of course, that if n is negative, that we're not going to take any action. We're going to panic in that state, in that case. And once we pass this, we know that our function input is okay. It's at least equal to 0. And here, if we look at our pseudocode, we don't declare a variable I outside of the loop. We somehow need to integrate this into the for loop. And we've thought about for loops abstractly as taking some action for a bunch of ranges of values. So we start I at 1 and we range it up to n, and each time for each possible value of I, we're going to take some action here. We're going to set p equal to p times I. So it's the same thing that the original factorial function was doing using a while loop, but we're not declaring this variable I outside of the loop. The question is, what syntax do we need in order to implement it? And I will set first p equal to 1 and then show you the syntax that Go uses for loops. Remember that Go uses the word for as a keyword for while, but it also uses for when we need a for loop. And so how is this going to work? We say for I colon equal to 1, I less than or equal to n, I plus plus, and we're going to have a bracket. And I'm going to explain those three statements that we have before the bracket that are separated by semicolons. So there are three statements here. And I'll just put these into comments. You don't feel like you have to, but I'm going to write them out. I colon equal to 1 is called the initialization step. That initialization step happens before anything else happens with the loop. So the first thing that happens is a variable I gets declared. That variable I is equal to 1. The second part of this for loop declaration is I less than or equal to n. And that is called the condition. That's the thing that we're going to check every time through the loop, including the first time that we go through the loop. That's the condition, as with a while loop, that we check whether we enter the block of the while loop. And it's the same thing here for a for loop. We check that condition. Is it true that I is less than or equal to n? If so, enter the loop. If not, bypass it. And then our final statement here, I++, Remember, I++ is equivalent to I equal I plus 1. We learned about that shorthand in the previous lesson. I'm going to start using it quite a bit. I++, though, is called the post condition. So the general structure of a for loop is to take these three components. You have something that happens at the start before anything happens in terms of the loop, which in this case is to declare I equal to 1. Then we have the condition that we check every time through the loop, which in this case is to check that I is indeed less than or equal to n. And then we have something that happens at the end of the while block, or at the end of the for block every time through the loop. So at the very bottom of this, think about every time we go through the loop, there is almost a hidden line of code that's I++ down here, corresponding to the post condition, meaning after everything happens within the loop, that's what we do, okay? So that's similar to what we had with our factorial function. So with our factorial function, note, we essentially had an I++, I equal to I plus 1 at the bottom of our loop, okay? So that we had this sort of post condition there. It's another way of thinking about what we were doing. In the meantime, I should say, what is it that we do every time through the loop? So what is it that exists within this for block? And within the block of the loop, all that we need to do is set p equal to p times I. We're multiplying the current value of p times I and updating the value of that variable p to be equal to the product of p times I. So that's something that should be familiar from what we've seen with our factorial function that used a while loop. And we're going to return p. Note that the bracketing is the same as with while loops. We need an opening bracket and a closing bracket enclosing the block of the loop. So every time through the loop, we check, is I less than or equal to n? If so, multiply the current value of p times I, update p accordingly, and in this way, we're going to multiply p by 1, and then 2, and then 3, and then 4, up to whatever the value of n is. If it's 10, up to 10. And so in that way, p is going to be 1 times 2 times 3, up to 10, and then eventually contain the value of 10 factorial, which we're going to return. Again, every time through the loop, we we increment I, so that's what we do at the end. And that's what our hidden line of code is there at the bottom that you can think about. All right. A quick note that not all three of these components of the for loop have to be present. You could have none of them present, which would be equivalent to while true. You could have only the condition present, and that would be equivalent to just a while loop. So that would be like while I less than or equal to n. And you'd need to assume that you've declared your I variable if you wanted to use that. But that's showing us why Go has this single keyword for just for and while loops, because if you just see a condition in a for loop, Go's able to automatically encode that as a while loop. But in this case, this is the typical case. This is a very typical kind of for loop in that we're going to declare a variable. We're ranging over up to n. So that variable will start at something. 1 is going to be a very common value, and it's going to go up to and including n, and then we're going to increase it each time through the loop and use it in some way. I think that that's all that I want to say in terms of introducing for loops. I think you can go ahead and start putting this into practice. So in the same way that we wrote a function to sum the first n integers, I would like you to write a function, and I'm just going to call it another sum. It takes an integer n as input and returns the sum of the first n positive integers with the caveat that it needs to use a for loop. So this is just practice writing a function using a for loop. And our function signature is going to be another sum. It's going to take an integer n as input. It's going to return an integer. And I'm going to continue writing this function, but I would suggest to you, give it a shot. Feel free to pause. And in the meantime, I'm going to continue on and show how to write this function. So the first thing that we want to do is to have our panic statement. And then the next thing that we want to do is to say, all right, well, we're going to need, in the same way that we did for our previous sum function, which I'd hope you have contained in this file if you followed the previous code along. We're going to need to store the final answer. So I'm going to copy that line of code up to another sum. And at the end, that's what I want to return. And now we need to say, all right, what is it that we want our initialization step to be? What condition do we want to check? And what post condition do we want to have? And I would say we can use the variable I or j or whatever we like. But however we do this, I'm going to use k. Our three components of the loop are going to be the same. So again, you're seeing this structure occurring in a different context, in a different function. And if you continue programming, you will see this all the time. We're ranging from a variable value of 1 up to n. So we set k equal to 1 as the initialization step. The condition that we're going to check is it the case that k is less than or equal to n? And every time through, we're going to increase k by 1. And here, instead of multiplying the current value of sum by k, we're going to set sum equal to sum plus k. And this also gives us an opportunity to practice our shorthand of simply saying sum plus equal to k. Take the current value of sum, add k to it, and set that value of sum equal to the resulting expression. So we use the shorthand sum plus equal to k to represent that. And that's another shorthand that I would like you to get comfortable with using. Even if you're not comfortable yet, it's always good to practice it because it will be, as you program in Go, something that you will eventually become very comfortable with and find second nature. One more story I would tell. This is a mathematical chapter, so I'm going to make one more mathematical aside, which is that there is a probably apocryphal, i.e. not exactly true, story about the 19th century mathematician Carl Friedrich Gauss, which is that his primary school teacher got annoyed with him and how precocious he was and how fast he was at solving problems. And so he set him the task of summing the first 100 positive integers, and he thought this could keep him occupied for at least a couple of hours. But he became frustrated that the young Gauss came back very quickly, almost immediately, with the correct answer of 5,050. What Gauss had noticed was that there is a faster way of producing the sum of the first n integers that doesn't require us to do a bunch of additions at all. Even though it seems like to sum the first n integers, we need to do 100 additions to sum the first 100 integers. That's not necessarily true. What Gauss had noticed is that there is a simple formula that will represent the sum of the first n positive integers. And I'm going to call our function Gauss sum because what Gauss noticed is that no additions need to be performed at all. We can simply return the expression n times n plus 1 divided by 2. And I will leave it open, if you don't know this story already, I will leave it open to you to figure out why that equation might give us the sum of the first n positive integers, why we don't need any looping or any sums at all. When you see it, it's a fun thing to notice, and I at least like to hope that the story about Gauss is true. He certainly went on to produce even more impressive mathematics, but in this case, it's a good example of what we see throughout this chapter, which is mathematics can sometimes give us very fast approaches that do not seem true or that are very much not obvious at first. And we're going to see that with Euclid's GCD algorithm that we're going to implement soon, as well as the sieve of Eratosthenes. And here's another little gem from mathematical history. I want to move on for now and make a stylistic point, which is we have two ways of writing a factorial function. We have a factorial function that uses a while loop. We have a factorial function that uses a for loop. We have a sum function, even though Gauss's sum function is the best. We have a sum function that uses a for loop. We have a sum function that uses a while loop. Is one better than the other? Are they basically equally good? They're both correct. And how I want to come at this is to say, let's look at our factorial function. And let's look at our another factorial function. I was going in the wrong direction. And what I'm going to do is print the current value of I. So I'll say I is currently, and then I'm going to print the value of I. And I want to do the same thing in my original factorial function that used the while loop down here. I'm going to say I is currently I. And then I'm going to save our code. And when I compile it, the code doesn't even compile. One of these lines of code is okay. The other one is not. So you'll note, even though I added two print statements, the one on line 80 is fine. The one on line 35 gives us a compiler error. And this allows me to make a point about why this compiles, but also to return back to something that we've seen in a previous code along and started to introduce a term called scope. So these functions seem very similar. They both have a p, they both have an I, we're incrementing I, we're checking the I is less than or equal to n, we're multiplying p times I and updating p accordingly. But this is what shows that the functions actually are not completely identical, because the scope of the variable I that we introduced in the factorial function using the while loop, well, it's declared here, which is in the main body of the function, which means that the scope of that variable, and the scope is just a fancy term for the lifetime. The lifetime or scope of that variable is the entire function. So it exists still down here were we to print it. However, in our another factorial function, the scope of variables that are declared, say as the initialization step of a for loop, the scope of those variables is only within the block of code representing the for loop. So for that reason, this code will not compile because I has already been destroyed. And you might look at this and say, okay, well, that's not great because I got a compiler error. But in fact, this demonstrates that using a for loop in this particular case, using a for loop is just a little bit better than using a while loop, because I should not exist outside of this part of the code. You might want to use a variable I in a separate context, and you don't want any issues with that because this is the only part of the code where I is used. In fact, we just need to increase I, check whether it's less than or equal to n, and use it in this multiplication. If this were a longer function, we wouldn't need access to I down here. And for that reason, using a for loop in this particular case I think it's a clear argument that it's better, only because of the scope of the variable I. I also want to congratulate you, moving on from that point, to say you've done a little bit of software engineering. So yay, can pat yourself on the back. You can put that on your LinkedIn and we can all go and get jobs at Meta, the best place in the world. But in all seriousness, this is the type of thing that software engineers do. They look at not just correct code, but code that's serving the correct purposes and that has, on this very low level, for instance, variables that have the appropriate scope. So as you progress as a programmer, these are the sorts of things to keep in mind, that there are stylistic approaches to programming, sometimes that you have decisions to make in terms of how to implement something, and we'll see those sorts of decisions pop up throughout the course. But this is a good, nice, simple example of how something as simple as variable scope can show that one way of writing a function is actually better than another. Before concluding, I would like to talk about for loops of a slightly different variety. And I'm going to write yet another factorial function. In fact, that's what I'm going to call it. Yet another factorial function. And I'm not going to introduce the function comment. I'll almost always do that throughout the course, but I think you know what this function is going to do. It's going to return n factorial. So I'm going to avoid that comment for now. And what I'm going to do is I'll have my panic statement first. I will have that. And then the way that I want to write my for loop here is I'm going to write a for loop that's backwards. So I'm going to declare my p equal to 1. Eventually that product variable is what we're going to return. But I'm going to declare I as not equal to 1, but instead, in my initialization step, I'm going to declare I to be equal to n. Then, every time through the loop, we're not going to check whether it's less than or equal to n, because I am actually going to decrement each time, and I'm going to check, is it the case that I is equal to greater than or equal to 1. So every time through, I'm going to decrease I by 1, which allows me to use what I told you about in the previous lesson, which is I minus minus, which is equivalent to I equals I minus 1. Every time I go through the loop, I'm going to take the same action. So the only difference here is instead of starting with 1 when I do my product, I'm going to start with n. But I'm still multiplying the same set of numbers. I'm still multiplying all of the positive integers between 1 and n into p subsequently as we go along. I'm just doing them in a different order. And we could ask the same sorts of questions. Is this, which is better, the previous version of another factorial or this one? I think this one is a little less intuitive, but I also wanted to point out that this is a perfectly fine way of writing this function, and you might have certain contexts where it makes sense to start at a higher value and decrease that because that's the natural way of considering your values. And in that case, I want you to be, make sure that you are aware you don't always have to write your for loops as starting a value at 1, increasing it by 1 each time, that sort of thing. You might pause for a moment, if you like, and think about how is it that another sum, the sum function that we wrote with a for loop, would need to change accordingly. And I'll also allow you to write a function called sum even as an exercise. So it takes as input an integer k, and what it's going to return is the sum of the all even positive integers up to and possibly including k. So give this shot a go. I'm going to write the function signature. You can pause whenever you like. I'm going to continue writing it, but before you follow along with me, feel free to pause and give it a go, because we're going to have sum even is going to take an integer k as input. It's going to return an integer as well. And think about how you might cleverly do this with a for loop. I'm going to avoid my panic statement for now. I should have a panic statement, but I'm just going to show, without that panic statement that I should add, the solution to this exercise. I don't know why I said sum equal to k. Set sum equal to 0, that's going to store our eventual value that we want, our eventual sum, which I will return. In the meantime, I need to say, okay, what is it that I'm doing? Say, for every even integer j between 1 and k, and I think I can say between 2 and k, 1 isn't even, set sum, I could say add j to sum. So one way that we could do it is to start j equal to 2, check whether or not j is less than or equal to k each time through the loop, increase it by 1 each time, and then within our for loop, we could have an if statement. That if statement would say, is it the case that j is even? And how can I check that? This is a way of applying our modulo percent operator, where we can determine whether a number is even if when we divide it by 2, we get a remainder of 0. And so we can check that. So we could say, if it's the case that j percent 2 is equal to 0, that remainder is 0 when we divide by 2, then the answer is yes. So we would add to the current value of sum whatever j is, sum plus equal to j. And that's a fine way of writing this function. If you are in the habit of writing for loops like this, where you start j equal to a value, you check it up to some point, and you increment it by 1 each time through the loop as your post condition. this will be a functional function. It's correct. But we can make a better version of this function, a little bit faster at least, I should say, by using a better specified post condition. That's all we need to change. So we're still going to start j equal to 2. We're still going to range j up to k, up to and possibly including k. But the one thing that we could do differently is to say, I don't need to consider 3, 5, 7, 9, 11. There's no reason for me to set j equal to those values ever. Why don't I just start j at 2 and then range it j equal to 2, 4, 6, 8, 10, 12, etc. And the way to do that is to, instead of doing j++, set j equal to j plus 2. So that way I know that there's no way that j can't be even, because it starts at 2 and it increases by 2 each time, so it's always even. And we just say j must be even, and that's a good thing. And so we set j equal to j plus 2, or, sum equal to sum plus j, or just sum plus equal to j. And we get our sum of all the even positive integers up to and possibly including k, which is what we wanted. We'll have a lot of opportunities to practice for loops throughout the course. That I can promise, because they're an immensely common structure that we are going to use over and over and over again in terms of programming. There's just one more point that I would like to make. We've written a lot of functions, but I want to go into func main and make one more little point, which is, let me declare a uint variable. I'll call it I. Let's call it count. And I'm going to set it equal to 10. Okay. And let's have a for loop. And that's been declared outside of the for loop. So I don't need an initialization step. I could have made that the initialization step, but I'm just using this as an example to show that we don't technically need an initialization step of the for loop. And we're going to say, we're going to do this for as long as count is greater than or equal to 0. And each time through, we're going to count minus minus. And I'm going to print count each time through. So we want this to be a countdown. 10, we're going to print 10, then 9, then 8, then 7, then 6, 5, 4, 3, 2, 1. We want to print 0. And then after that's the case, we want it to go to a negative number. And we're going to print blast off. Okay, so it's just going to be a countdown. Now, there's no delay here. And so if we were going to print these statements, they're going to print very, very quickly. But we're at least printing out 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, blast off. And I've saved my code, and I'm going to compile it, and then run it. And this does not look good. This is a whole lot of numbers printed that have nothing to do with 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We're printing some very, very large numbers. But they are decreasing, and that's a good thing. And so you might pause for a second and think about, what do you think exactly is going on here? I'm going to Control-C this. It's another good example of where you definitely want to Control-C a program because it's out of control. And the last thing that we printed is 184467440737025595523. That might seem kind of familiar to you if you followed some previous code alongs. And we can think about what is going on here. The word overflow or underflow might be going off in your head. The reason why is we declared the count variable to be an unsigned integer. And the values that unsigned integers take range from 0 to the largest possible unsigned integer. As you go through this, if I were to scroll far enough up in the terminal, you would see that 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 does indeed get printed. But that what happens at the end of this process is, when count is equal to 0, we print 0, good, and then you have at the bottom, think about the hidden count minus minus. And you're thinking about this as going to -1, right? Because when we count, we go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, -1. And that -1 would no longer be greater than or equal to 0, which is good. So we would no longer enter the for loop, and we would print blast off. That's the desired behavior. The problem is that if you have an unsigned integer, and that unsigned integer is equal to 0, and you subtract 1 from it, Go says, well, there is no such thing as a negative unsigned integer. And so the best thing that I can do when I subtract 1 from 0 is to go to the largest possible unsigned integer. So we've underflowed and gone to the maximum possible unsigned integer, which is why you're seeing really big numbers get printed. And the process is going to continue because it's always going to be true that an unsigned integer is greater than or equal to 0. So this is not like expected behavior, but it is the behavior that makes sense. And that is the case because we simply don't allow unsigned integers to have negative values. I will make a point, though, that this is also presumably kind of annoying because we had code that seemed like it probably should work. And I will advise you to just be careful with using unsigned integers. In practice, I think you'll see throughout the course that I typically will just use integers. That's a type that's going to work for us, and we can always panic if we need to when taking an input, or have some sort of error message for giving a negative input where it needs to be positive. We can handle things in that way. And we might get some strange behavior if we try to use unsigned integers. There's even more to that story, and in fact, some programming languages, most notably Java, don't even allow support for unsigned integers. The only type of integer they're going to allow you to have is an integer that has a sign associated with it. Whether it winds up being exclusively positive is something you can handle in another way. So with that, we conclude really the fundamental basics of Go. So I hope you're proud of yourself for making it this far. We've learned quite a lot, and some of these basics can be the trickiest part of learning how to program. Now we get to do more and more fun things. And we'll return to Euclid's algorithm, which I presented in the previous code along and showed you the pseudocode for it and said that you're really ready to go ahead and try to implement that algorithm yourself. In the next code along, we're going to come back to GCD algorithms and say, how well could an old algorithm perform compared to a more intuitive approach. And we're also eventually going to look at prime finding algorithms too. And so we're going to get to wrap up this chapter and learn and see some fun things and see that these algorithms really are actually pretty cool. So, but you'll have to stick with me for then. Until now, that's going to wrap up today. I hope you had fun. I sure did. And until I see you next time, happy coding.